Why does the universe have a speed limit? It's one of those questions that seems simple at first, but once you dig in, it unravels into one of the deepest mysteries of existence. Why can't we just build a faster rocket, pump in more energy, and zoom across the galaxy at any speed we like? Why does the universe seem to say no, no matter how hard we try? So, if you want the answer to that question, watch this video till the end and subscribe to the channel. Let's begin. The cosmic speed limit is one of the most profound and beautifully strict laws that govern our universe. An invisible barrier that defines the boundary between what is possible and what is not. It's not a rule humanity invented, nor one that can ever be broken with clever technology or brute force. It's the law of nature itself, written into the blueprint of reality. That limit, the fastest anything can move through space, is the speed of light in a vacuum, precisely 299,792 kilometers per second, or about 186,000 miles per second. To truly grasp that number, consider this. Light can circle the entire Earth more than 7 times in just 1 second. When you flick on a lamp, those photons hitting the wall do so virtually instantaneously, yet they still obey the same cosmic limit as every beam of starlight crossing interstellar space. But here's what makes this so astonishing. The speed of light isn't just fast, it's final. It's the ultimate speed, the top gear of the universe, the upper bound that no signal, no object, and no bit of information can surpass. Everything, from the hum of your Wi-Fi router to the cosmic ripples of gravitational waves caused by colliding black holes billions of light years away, must obey this same rule. Nothing goes faster, nothing even ties with it except the light itself and other massless phenomena. This limit is universal. It applies in every corner of the cosmos, in every galaxy, and in every instant of time. There are no exceptions, no secret shortcuts, no hidden loopholes. The universe enforces it with absolute precision. And what's even more fascinating is that this speed, this magical number, doesn't depend on you. Whether you're standing still, racing in a spaceship at half the speed of light, or orbiting a black hole, when you measure the speed of light, it's always the same. That's not just strange, it's revolutionary. Before Einstein, scientists assumed that speeds should simply add up. If you're on a moving train throwing a ball forward, the ball's speed is your throwing speed plus the train's speed. Logical, right? But light refuses to play by those rules. If you're on a spaceship moving near light speed and shine a flashlight forward, the light from your flashlight doesn't move away from you at your speed plus light's speed. It still travels away from you at exactly c, the same constant speed it always does, no matter what. The universe somehow adjusts space and time themselves to make sure that c never changes. That constancy is one of the most important clues to understanding the true nature of space-time. To appreciate how staggering that is, think about how this rule governs communication across the cosmos. When NASA sends a signal to a Mars rover, the radio waves, which are just light waves at a different frequency, take between 5 and 20 minutes to arrive, depending on the distance between Earth and Mars at that time. When astronomers observe a galaxy 10 billion light years away, the light they see left that galaxy 10 billion years ago, long before Earth even existed. The finite, unchanging speed of light doesn't just limit how fast we can travel, it limits how far back in time we can see. Every time we look at the night sky, we're not seeing the universe as it is right now, but as it was. The speed limit turns the cosmos into a kind of time machine, one that always looks backward. But this rule doesn't just govern light. It applies to everything that transmits energy or information. Gravitational waves, the ripples in space-time created by massive events like merging black holes, also travel at the speed of light. So do all massless particles, like the photon and the gluon, though the latter is trapped within atoms and never travels freely through space. Even our most advanced theories of quantum fields, the frameworks underlying all known forces, rely on the assumption that nothing can send information faster than c. If this rule were even slightly violated, if something could outpace light by even a fraction of a percent, the universe's consistency would shatter. Causality, the idea that causes precede effects, would break down, and paradoxes would run wild. To many people, the speed of light sounds like a property of light itself, but physicists understand it differently. The speed of light is not about light, it's about the universe. Light just happens to be the thing that moves at this speed because it's massless. The real truth is that c defines how space and time are knitted together. It's not a speed in the everyday sense, like miles per hour or kilometers per second. It's a fundamental ratio, a constant of nature that tells us how much space is equivalent to how much time. It's the yardstick of reality, the scale on which both the ticking of a clock and the stretching of a meter are built. If the speed of light were different, even by a small amount, everything about our universe would change. The behavior of atoms, the lifespan of stars, the strength of gravity, and even the chemistry that makes life possible would all be altered. The speed of light sets the rhythm of the cosmos, the tempo of time itself. It's not just the universe's fastest speed, it's the defining speed. The way space expands, the way time flows, and the way energy transforms are all built around this single, immutable number. It's as if the entire symphony of the universe is composed in the key of C. So when we say that nothing can go faster than light, we're not merely making an observation about photons. We're acknowledging the most fundamental constraint reality imposes. This is the cosmic speed limit, not because light decided to move that way, but because the very fabric of space and time demands it. Light simply travels at the only speed the universe allows for things that are massless. Everything else, every planet, ship, particle, or person, must move slower, always playing catch-up in a race they can never win. And this brings us to the deeper question: why does this speed limit exist at all? To answer that, we need to dive into the mathematics and insights of one of the greatest revolutions in human thought. A theory born in 1905 that reshaped the way we think about motion, time, and the universe itself. When we talk about the speed of light, it's easy to imagine we're just talking about how fast a beam of light travels through space, a property belonging to light alone. But in truth, this idea runs far deeper. The speed of light is not just about light, it's a fundamental constant of nature, represented by the letter c. This c, short for celeritas, the Latin word for swiftness, is one of the most important symbols in all of science. It appears in the equations that govern everything from electromagnetism to relativity to quantum mechanics. It's not merely a speed, it's the cornerstone that connects space, time, energy, and matter into one unified reality. In physics, constants like c are not just numbers. They are the universe's unchanging truths, the bedrock values that stay the same everywhere, every when, regardless of conditions. The gravitational constant, g, Planck's constant, h, and the elementary charge, E, all play foundational roles in how nature behaves. But c stands apart. While others describe the strength of interactions or the scale of the microscopic world, c describes the very relationship between space and time themselves. It's the ratio that binds the fabric of the cosmos together. It tells us how distance translates into duration. How far light travels in 1 second defines what a second means in physical terms. It's as if the universe itself uses c as the speed at which it updates reality. To truly understand what c represents, we have to shift perspective. Before Einstein, scientists believed that light's speed was tied to its medium, that it might move faster or slower depending on what it passed through, like sound waves in air or water. But experiments, most famously the Michelson-Morley experiment in 1887, proved otherwise. No matter how they measured it, no matter the direction of Earth's motion through space, the speed of light remained the same. This baffled scientists because, according to classical physics, speeds should add or subtract depending on your motion. If you run toward a beam of light, shouldn't you measure it as moving faster? If you move away, shouldn't it seem slower? But nature doesn't play by those rules. The speed of light is constant for everyone, always the same value, no matter who measures it or how fast they're moving. That single, unyielding fact was the key that unlocked Einstein's theory of relativity, and with it, a radical new understanding of the universe. Einstein realized that if light's speed never changes, then something else must, and that something was space and time themselves. They must stretch, shrink, and warp so that c always stays the same. This meant that the speed of light wasn't just a property of light. It was a property of spacetime. The constant c isn't about how light moves through space. It's about how space and time define motion at all. In this way, c acts as a conversion factor between two dimensions we normally think of as separate, space and time. It allows physicists to express time in terms of distance or distance in terms of time, because in the universe's language, they are two sides of the same coin. 1 second of time is equivalent to about 299,792 kilometers of space. That's how far light travels in 1 second. When you multiply a time interval by c, you get the corresponding distance. When you divide a distance by c, you get the corresponding time. The units may differ, but c unites them, showing that what we call space and time are not separate realms, but dimensions of one continuous entity, space-time. The presence of c in physics goes far beyond relativity or optics. It appears in Maxwell's equations, the laws that describe how electric and magnetic fields interact. When James Clerk Maxwell combined these equations in the 19th century, he discovered that they predicted electromagnetic waves traveling at a specific speed, and that speed matched perfectly with the measured speed of light. That revelation led him to propose something revolutionary. Light is an electromagnetic wave. It was the first time anyone realized that c was more than a number. It was a fundamental feature of nature's forces. But perhaps the most famous place c appears is in Einstein's iconic equation, E equals mc squared. Here, c squared, the speed of light squared, acts as the bridge between mass, m, and energy, E. It tells us that a tiny amount of mass can be converted into an enormous amount of energy because the conversion factor, c squared, is immense. This relationship powers the stars, fuels nuclear reactions, and underlies the energy that drives the cosmos itself. Without c, mass and energy would be unrelated, two disconnected quantities. With it, they become different forms of the same essence, interchangeable aspects of reality's most fundamental currency. Even more subtly, c governs the limit of information transfer in the universe. In every physical law that deals with cause and effect, from quantum field theory to thermodynamics, c sets the upper bound on how quickly any signal can propagate. Nothing can communicate faster than light, because information itself, the thread that ties one event to the next, is woven at that speed. If you could somehow send a message faster than c, you'd be sending it backward in time in some reference frames, unraveling the very concept of causality. C doesn't just limit speed, it protects reality from paradox. In natural units, a system physicists often use for simplicity, c is set to 1. That's not because we're ignoring it, but because it's so fundamental that it defines the very scale of measurement. Space and time are measured in the same units when c equals 1, meaning the universe itself treats them as one unified thing. This shows just how deeply c is embedded in the laws of existence. It's not a speed we measure, it's the framework that allows measurement at all. So when we say the speed of light, we're not merely describing how fast light moves. We're invoking the constant heartbeat of the universe, the rhythm at which time and space exchange identities, the conversion rate between matter and energy, and the maximum tempo of causality. C is not something within the universe, it's something the universe is built upon. It's the scaffolding of reality, invisible yet absolute, a constant reminder that everything, from the motion of particles to the ticking of clocks, dances to the same universal tempo. And now that we understand what C truly represents, we can explore how one man's insight turned this constant into the key to understanding space, time, and the nature of motion itself. When Albert Einstein introduced his special theory of relativity in 1905, he didn't just redefine physics, he redefined reality. At the dawn of the 20th century, science stood at a crossroads. The mechanical universe envisioned by Isaac Newton, a vast clockwork governed by predictable laws of motion, had served humanity for more than 2 centuries. Space and time were thought to be absolute, unchanging stages upon which the drama of the cosmos played out. Space was the vast emptiness through which objects moved, and time was the steady, universal tick of a cosmic clock, the same everywhere and for everyone. If you were to ask physicists in the year 1900 what could possibly challenge that view, most would have said nothing. And yet, in 1905, a 26-year-old patent clerk named Albert Einstein would change everything. His special theory of relativity didn't just tweak Newton's laws, it tore them down and rebuilt our understanding of reality from the ground up. Einstein's genius lay in daring to question the most basic assumptions. What if space and time were not separate things? What if the measurements of distance and duration, once thought to be fixed and universal, could actually depend on your state of motion? What if the very fabric of reality flexed and warped so that the speed of light remained constant for everyone? These were the questions that led him to one of the most elegant and revolutionary insights in all of human history. Einstein began by taking seriously what others tried to dismiss, that the speed of light, c, is constant in every frame of reference. The Michelson-Morley experiment had demonstrated that no matter how fast Earth moved through space, the measured speed of light never changed. Instead of trying to explain that away, Einstein accepted it as a fundamental truth and asked, what would have to be true about space and time for this to make sense? His answer was breathtaking. Space and time are not separate entities at all. They are 2 inseparably linked aspects of a single, unified continuum called spacetime. In this new vision, motion through space affects motion through time. The faster you move through space, the slower you move through time. Space and time are not rigid, absolute frameworks. They are elastic and interdependent. They bend and adjust so that the speed of light remains the same for everyone, no matter how fast they're traveling. This concept defied centuries of common sense. In everyday experience, if 2 people measure a moving object, they'll get different speeds depending on their motion. But Einstein showed that when it comes to light, nature doesn't allow that. Instead, the universe itself compensates. Distances shrink, time stretches, and simultaneity, the idea that 2 events can happen at the same time, becomes relative. This was the birth of relativity, the realization that space and time are woven together into a 4-dimensional fabric where events are defined not just by where they happen, but when they happen. Every object, every particle, every photon follows a path through this space-time, and the speed of light c, is built directly into the geometry of that path. It's not merely a limit imposed on motion, it's a structural feature of the universe's design. If space-time were a piece of fabric, c would be the tightness of the weave, the constant that determines how space and time transform into one another. To visualize this, imagine space-time as a vast grid. Each point represents both a location in space and a moment in time. When something moves, it traces a line through this grid, its world line. For something moving slowly, the world line tilts only slightly through time, moving mostly upward, representing the steady passage of time with little spatial change. For something moving faster, that world line leans further, meaning it covers more space in less time. But there's a catch. No matter how much you tilt it, that line can never reach a 45-degree angle, because that angle represents the speed of light. C is the slope that defines the boundary between possible and impossible motion. Anything with mass must have a world line less steep than that, slower than light, while anything massless, like a photon, moves along that boundary. The universe itself enforces this geometry. Before Einstein, space and time were thought to be passive, empty containers in which events occurred. After Einstein, they became dynamic, interactive participants in the story of reality. They could bend, stretch, and even warp in response to energy and motion. Special relativity was the first step in revealing that truth. It told us that there is no universal now that applies to everyone. Two observers moving at different speeds will disagree on what events are simultaneous. This isn't a trick of perception. It's how the universe truly works. Time and space adapt so that all observers, no matter their motion, measure the same. See Einstein's equations also revealed that mass and energy are two sides of the same coin. The famous E equals mc squared emerges directly from this new understanding of space-time. It tells us that mass is just a concentrated form of energy, and that energy has mass. The c squared in that equation, the square of the speed of light, acts as the conversion factor between them. In other words, c doesn't just appear in the laws of light or motion. It's embedded in the very identity of matter and energy themselves. This was more than a theory about moving clocks or fast spaceships. It was a redefinition of reality. Time no longer flowed like a universal river. It became something personal, tied to your speed and direction through the cosmos. Space was no longer a silent backdrop. It became a living structure that told matter how to move, and was, in turn, shaped by that movement. Einstein's work took what was once considered separate, space and time, and revealed their unity. The universe, it turned out, wasn't built on absolutes, but on relationships. And this was only the beginning. Special relativity was the spark that ignited the modern age of physics. It paved the way for general relativity, where Einstein extended these ideas to include gravity, showing that massive objects like stars and planets bend space-time itself. But even before that great leap, special relativity alone transformed everything. From how we think about motion to how we understand the limits of speed, the flow of time, and the structure of existence. Yet, Einstein's theory also raised a new, fascinating question. If space-time itself imposes a cosmic speed limit, what happens when something tries to reach it? Why can light move at this ultimate speed while everything else falls short? What makes that barrier so unbreakable? The answers lie in the strange and beautiful consequences of relativity itself, where energy, mass, and motion intertwine in ways that defy ordinary logic. When Einstein revealed that the speed of light is the cosmic limit, the ultimate boundary woven into the very fabric of space-time, he also revealed a deeper truth about motion, energy, and the nature of matter itself. Nothing that has mass can ever reach the speed of light. Not because we haven't built a powerful enough engine, but because the very laws of physics forbid it. The closer an object with mass gets to light speed, the harder the universe resists its acceleration, until reaching that limit would require something truly impossible: infinite energy. To understand this, imagine what happens when you try to make something go faster. At low speeds, acceleration is easy. Push a ball and it rolls. Fire a rocket and it gains speed. Each bit of added energy gives a clear and predictable increase in velocity. But as an object moves faster and faster, something subtle begins to happen. Its kinetic energy grows not just linearly, but exponentially. In the familiar world of slow speeds, we're used to the simple idea that energy equals 1/2 the mass times the velocity squared. But relativity changes the rules entirely. As speed increases, not only does kinetic energy rise, the mass-energy relationship itself starts to shift. The object doesn't gain rest mass, but from the perspective of an outside observer, it behaves as if it's becoming heavier, harder to push, and more resistant to further acceleration. Picture this. You're piloting a spaceship, accelerating steadily, burning fuel to push ever closer to light speed. At first, your acceleration feels normal. Each second you gain more speed. But as you approach a significant fraction of light speed, you begin to notice something strange. The same amount of thrust that once made your ship leap forward now gives you a smaller and smaller increase in velocity. You keep feeding your engines more energy, but your gains start to shrink dramatically. From your point of view, your engines roar, your fuel burns, and your energy output skyrockets, yet your speed asymptotically creeps toward light speed without ever reaching it. Why? Because according to Einstein's equations, the faster something moves, the more of its energy goes into bending the very fabric of space and time, rather than simply increasing speed. In simpler terms, motion changes the way energy and time interact. As you get closer to light speed, the universe begins to push back, not physically, but fundamentally. The energy you're adding doesn't translate directly into more speed. It translates into changes in how time and space behave for you. The effort of pushing against space-time's limit becomes monumental. Mathematically, if you were to express the energy of a moving object in words rather than symbols, it would go something like this. The total energy of an object equals its rest energy, the energy it has simply by existing, multiplied by a correction factor that depends on its speed relative to the speed of light. That correction factor starts small when the object is slow, but as the object approaches light speed, that factor grows without bound. It climbs higher and higher, faster than any engine could ever compensate for, until it shoots toward infinity as speed approaches c. In other words, the closer you get to light speed, the more energy you need, and that required energy grows faster than you could ever supply. So even if you had the most advanced spaceship imaginable, powered by the total energy output of all the stars in the universe, you would still never make it to light speed. You could reach 90% of it, maybe 99.9%, or even 99.999999%. But each step closer demands exponentially more energy than the last. To actually reach light speed, you'd need infinite energy. And since infinity doesn't exist in any physical sense, nature draws a hard line there. It's not that you shouldn't go faster, it's that you can't. The structure of reality itself won't allow it. And this barrier isn't just about energy. The closer you get to light speed, the more your experience of time and space begin to distort. To an outside observer, your ship's clock slows down, your lengths contract, and your energy appears to skyrocket. These effects don't just make it harder to move faster. They are the mechanism by which the universe maintains its speed limit. Space-time adjusts itself to ensure that no matter how much energy you pour into motion, you can never exceed that ultimate velocity. It's as though the fabric of reality itself stiffens against your effort, growing infinitely rigid as you near the boundary. There's another way to visualize this. Think of light speed as the edge of a cosmic ocean. Everything with mass floats within the waves. Planets, particles, people, ships. As you pour in energy, you can make bigger and bigger splashes, moving faster and faster, but you'll never leave the water entirely. Light, on the other hand, isn't a swimmer at all. It's the ocean itself, the ripple that moves through it naturally at its maximum possible speed. You can mimic it, you can chase it, but you'll never become it. This insight reveals something profound about the way the universe is constructed. The speed of light isn't just a number or a limit. It's a boundary between two kinds of existence. On one side are all the things that have mass, everything that can age, everything that can experience time. On the other side are things like light and other massless particles that always move at sea. They don't experience time as we do. From their perspective, there's no before or after, no aging, no waiting. For a photon, the journey from one end of the universe to another happens instantaneously, because for it, time doesn't pass at all. So when we say nothing with mass can reach the speed of light, what we're really saying is that mass and time themselves are tied together in a dance that can't cross that threshold. To reach C would mean shedding not only your mass, but your experience of time entirely. It would mean leaving behind the universe as we know it, a place where cause leads to effect, where events unfold in sequence, where motion has meaning. The cosmic speed limit isn't a barrier meant to frustrate us. It's the very thing that keeps reality coherent. It preserves causality, keeps energy and mass consistent, and ensures that every observer, no matter where they are or how fast they move, experiences a universe that makes sense. The impossibility of reaching light speed isn't a shortcoming of physics, it's one of its greatest triumphs. It's the rule that keeps everything, from galaxies to atoms, behaving in harmony. But what happens as we keep trying? As we pour in more and more energy, inching closer to the unbreakable limit? The challenge doesn't just grow, it becomes impossible. The closer we get, the harder the universe pushes back, until even infinite effort could never carry us one fraction of a second faster. And that brings us naturally to the next revelation, the idea that the universe quite literally resists your motion the closer you come to the cosmic speed limit. The closer you get to light speed, the harder it gets. Not just in the sense of difficulty, but in the sense that the very fabric of the universe seems to push back. It's as if reality itself resists your motion the faster you go. Imagine piloting a spaceship through the deep black of interstellar space. At first, your engines roar to life and acceleration comes easily. You feel the thrill of motion as the stars ahead begin to drift, the sense of power as speed mounts. But as your ship edges closer to a significant fraction of the speed of light, something extraordinary happens. Every bit of additional speed demands more and more energy, far more than before, and the universe begins to act like an invisible force, pushing back against your progress. In the beginning, at low velocities, motion behaves exactly as we expect from our everyday experience. Push something and it moves faster. Double the energy and you roughly double the speed. It's intuitive, it's familiar, it's the classical world of Newton's mechanics. But that neat simplicity starts to crumble once your speed climbs to a meaningful fraction of the cosmic speed limit, say 10%, 50%, 90% of light speed. At that point, Newton's comforting equations no longer tell the truth. The rules of relativity take over, and they reveal that acceleration is no longer a straightforward exchange between energy and velocity. Instead, the faster you move, the more stubbornly spacetime resists any attempt to make you go faster still. Imagine this scenario. You're aboard that spaceship again, engines blazing, trying to cross from one star to another. You begin by accelerating easily. A little push adds a noticeable increase in speed, but as your velocity climbs, the returns on your effort start to shrink. Each burst of fuel adds less and less to your actual speed. You pour in more energy, but your velocity barely budges. From your perspective inside the ship, you're doing everything right. The engines are firing perfectly, and your instruments show massive energy output. But from the universe's perspective, you're pushing against the deepest limits of what's physically possible. Here's the key idea. As your velocity approaches light speed, your kinetic energy doesn't just increase, it skyrockets at an accelerating rate. The faster you move, the more energy you need for even the tiniest nudge forward. This isn't just a matter of diminishing returns, it's a wall of impossibility. Nature isn't just making it hard, it's making it impossible. As you push closer to the speed of light, the amount of energy required to add even the smallest bit of extra velocity grows so rapidly that it heads toward infinity. In the language of physics, if you were to express the relationship without using symbols, it would sound like this. The total energy needed to move increases dramatically as your speed nears light speed, and at that ultimate threshold, the energy requirement becomes infinite. And infinity, in physics, isn't just a big number. It's a boundary that cannot be crossed. It means that no matter how much energy you gather, even if you harness the entire output of every star in every galaxy, it still wouldn't be enough. The universe has built-in safeguards against breaking its own rules. So when scientists say that nothing with mass can reach light speed, they're not being pessimistic. They're describing a truth as fundamental as gravity or time itself. The laws of physics simply will not allow it. There's a poetic irony here. The very thing that makes motion possible is also what limits it. The energy you put into moving faster doesn't vanish. It transforms, but not in the way you might expect. Some of it goes into increasing your momentum, but as you near light speed, much of it begins altering how time and space behave around you. To the universe, you're not just speeding up, you're warping space-time itself through your motion. Your clock ticks more slowly compared to someone at rest. Your lengths contract in the direction of travel. Energy stops behaving in the neat, linear ways we're used to. You're no longer just a traveler through space. You're a participant in the cosmic geometry of space-time itself, caught in a struggle against a limit that defines existence. From a certain perspective, this resistance can even be seen as the universe maintaining order. The speed of light, this absolute limit, isn't an obstacle to exploration. It's a framework for coherence. If objects with mass could accelerate past it, chaos would ensue. Causality, the sacred rule that cause comes before effect, would crumble. You could theoretically send signals into the past, witness an event before it occurred, or have an effect precede its cause. Reality, as we know it, would disintegrate into paradox. So, as frustrating as it may seem to our imaginations, the fact that nature pushes back against our attempts to reach light speed is a blessing in disguise. It preserves the integrity of the universe. You can visualize this struggle through a more intuitive analogy. Think of trying to move through a thick fluid, say, swimming through syrup. When you move slowly, it's easy. As you increase your speed, the resistance grows. Eventually, you reach a point where no amount of strength can make you go any faster because the resistance becomes overwhelming. The difference, of course, is that the syrup's resistance is physical, the viscosity of a fluid. The universe's resistance at near light speeds, however, isn't due to any medium you're pushing through. It's due to the geometry of space-time itself. You're not colliding with something external. You're colliding with the limits of how energy, motion, and time can coexist. Even at speeds achievable by modern technology, we can already measure the beginnings of this effect. In particle accelerators, scientists regularly push subatomic particles, like protons or electrons, to incredible speeds, sometimes to more than 99.9999999% of light speed. At those velocities, the particle's effective energy increases by millions of times their rest energy. The machines consume unimaginable amounts of power just to give them the tiniest additional boost. And still, none of them ever reach light speed. The closer they get, the more energy it takes, until the curve of possibility stretches endlessly upward. In this sense, the speed of light is both a wall and a mirror. It shows us not how limited we are, but how profoundly structured the universe is. It's a reminder that energy, mass, and motion are bound together in an intricate dance, where every step follows cosmic rhythm. The universe doesn't just set a limit, it defines reality through it. So when we say, imagine pushing a spaceship faster and faster, at first it's easy, but near light speed, the universe pushes back, we mean exactly that. Every bit of extra speed demands exponentially more energy, until eventually you'd need an infinite amount to go any faster. That's why nothing with mass can ever reach the speed of light. The laws of physics simply won't let it. It's not a failure of technology, not a challenge waiting to be overcome, but a cosmic truth carved into the very shape of existence. And this leads us naturally to the next wonder. If time and space themselves shift as we approach the speed of light, what does that mean for those who dare to travel near it? How does the passage of time itself change for them compared to us? The answer opens one of the most mind-bending doors in physics, the phenomenon known as time dilation. Time dilation, two words that sound like science fiction, yet describe one of the most astonishing, proven realities of our universe. It's not an illusion, not a mathematical trick, and not merely a theory. It's something that actually happens, measurable, observable, and profoundly real. As an object moves faster and faster, time itself slows down for it relative to someone who remains at rest. The faster you travel through space, the slower you travel through time. This is one of the strangest and most beautiful consequences of Einstein's theory of relativity, and it reveals something extraordinary. Time is not absolute. It's flexible, elastic, and deeply intertwined with motion. To grasp this, let's return to that spaceship hurtling through the void. You're the pilot, approaching speeds close to the cosmic speed limit, perhaps 90% or 99% of the speed of light. From your perspective inside the ship, everything feels normal. Your heartbeat keeps its rhythm. Your watch ticks second by second. Your body functions as it always does. You feel time flowing naturally. But to an observer watching you from Earth, your time is no longer flowing the same way. They see your clock ticking slower, your movements unfolding in drawn-out, deliberate slowness. If they could somehow see your heart monitor, each beat would appear to take longer than before. To them, you're living life in slow motion. And yet, from your perspective, nothing feels different. That's the beauty and the strangeness of relativity. Both perspectives are equally valid. Both are true. You're moving through space-time differently, so your slice of time is not the same as theirs. Time itself bends to accommodate your motion, ensuring that the speed of light remains constant for everyone. The faster you move, the more dramatically time stretches for you compared to someone stationary. Even here on Earth, we can measure this effect. Astronauts aboard the International Space Station are moving at nearly 28,000 kilometers per hour relative to us. It's nowhere near light speed, of course, but even at that velocity, the difference is real. The astronauts' clocks tick slightly slower than those on Earth. Over the course of 6 months, they age just a fraction of a second less than the people they left behind. It's a tiny effect, imperceptible to human senses, but measurable with modern instruments. The same principle applies to high-speed particles in physics experiments, where we observe unstable particles living longer when they move faster. It's not magic, it's time dilation in action. Now, imagine scaling that effect up to near-light speeds. If you could somehow accelerate your spaceship to 99.999% the speed of light, time dilation would become mind-bending. From your perspective, your journey to a distant star might take only a few months, but for those back on Earth, decades or even centuries could pass during your trip. When you returned home, you might have aged only a few years, while everyone you knew would have grown old or long passed away. You would have, in essence, traveled into the future, not by jumping through time like in fiction, but by experiencing time at a different rate. This phenomenon isn't speculative, it's built into the structure of spacetime. The equations of relativity, when expressed in words, tell us that as your speed increases, the passage of time for you slows in such a way that it can never stop entirely, but it can slow without limit as you approach the speed of light. Time for you stretches thinner and thinner, like taffy pulled close to breaking, until from an outside perspective, it nearly freezes. At light speed itself, time for a photon doesn't flow at all. From its perspective, if we could imagine such a thing, its entire journey from emission to absorption happens instantaneously. For light, there is no waiting, no delay, no passage of moments. That's what it means to exist at the cosmic speed limit. This concept challenges one of our deepest intuitions, that time is universal, the same for everyone, ticking equally everywhere in the cosmos. For centuries, we believed that time was an independent backdrop, an ever-flowing river unaffected by motion. Einstein shattered that notion completely. Time, he showed, is woven together with space into a single, malleable fabric, space-time, and how you move through one affects how you move through the other. When you move faster through space, you move slower through time. It's a trade-off written into the very geometry of reality. One way physicists like to explain it is through the idea of a space-time budget. Every object in the universe moves through space-time at the same total rate, the speed of light, c, but that motion can be divided between space and time. When you're at rest in space, you're moving entirely through time, aging at the normal rate, second by second. But when you move through space, part of that total motion is spent in the spatial direction, leaving less for the temporal one. So the faster you move through space, the slower you move through time. This isn't a metaphor, it's literally how space-time behaves. What's even more awe-inspiring is that this isn't confined to high-speed travel through space. Gravity, which according to Einstein's later work in general relativity, is just the warping of space-time by mass, also slows down time. Clocks on the surface of the Earth tick ever so slightly slower than those at high altitude because Earth's gravity curves space-time. This means time flows differently for every point in the universe, depending on speed and gravity. It's a deeply humbling realization. There is no single, universal now. Time dilation has been tested and confirmed countless times. In 1971, the Hafele-Keating experiment flew atomic clocks around the world aboard commercial jets, comparing them to synchronized clocks left on the ground. When the planes landed, the clocks showed tiny but measurable differences, exactly as Einstein predicted. Every GPS satellite orbiting Earth today must account for both gravitational and velocity-based time dilation. Without those relativistic corrections, GPS signals would drift by kilometers every day. So even though these effects seem abstract, they shape the technology and precision navigation systems we rely on daily. But it's when we look to the stars that time dilation takes on its most poetic form. It means that in principle, space travel to distant worlds isn't bound just by distance. It's bound by time itself. For travelers who could approach the speed of light, entire galaxies could be reached within a lifetime from their perspective, even though millions of years might pass on Earth. They would become time voyages, skipping across the cosmic ocean while the rest of the universe ages around them. Time dilation doesn't just change our understanding of motion, it changes our understanding of existence. It tells us that time is not an external force we move through, but part of the very essence of the universe, sensitive to our movement and the curvature of space itself. It reveals that we are all, quite literally, shaping time as we move. And this leads naturally to its companion phenomenon. If time can slow down at high speeds, what happens to space itself? Does it remain rigid and unchanging, or does it too transform under the strain of motion? The answer is just as breathtaking. Space itself begins to contract. Distances shrink, worlds draw nearer, and the universe bends before the traveler who dares to approach the speed of light. This next wonder of relativity is known as length contraction, the mysterious squeezing of space itself. From the traveler's point of view, something extraordinary happens as their ship approaches the speed of light. The universe itself begins to shrink. Distances that once stretched across light years seem to collapse. Stars that were impossibly far away now appear within reach, and the vast gulf of space ahead folds inward as if the cosmos were squeezing itself to make room for the traveler's motion. This phenomenon, called length contraction, is one of the most stunning predictions of Einstein's relativity, and like time dilation, it's not a trick of perception or an illusion. It's a real, measurable effect, a reshaping of reality itself that depends entirely on how fast you're moving. To someone watching from a distance, say a scientist observing from Earth, the ship seems to be moving faster and faster, its time slowing relative to their own. But to the traveler inside the ship, it's not their clock that's changing. It's space that's being distorted. The faster they go, the more the distance to their destination appears to contract. From their frame of reference, they're not traveling millions of kilometers per second through a vast, unchanging void. Instead, the universe itself is bending and compressing around them. This might sound like science fiction, but it's an inevitable consequence of how space and time intertwine. In relativity, there's no such thing as absolute distance or absolute duration, only relationships between observers. When you move close to light speed, those relationships shift. To keep the speed of light constant for everyone, space and time must adjust in perfect harmony. As your motion increases, time slows for you, that's time dilation, and space in the direction of your travel shrinks proportionally, that's length contraction. Both effects are not separate phenomena, they're two sides of the same cosmic balancing act. Imagine you're racing toward a distant star system 20 light-years away at 99.9% the speed of light. To someone watching from Earth, the trip will take just over 20 years. But to you, the traveler aboard the ship, time is flowing more slowly. And not just that, the distance itself has contracted. From your perspective, the star system is no longer 20 light-years away. It might be only a few light-years, or even less, depending on your speed. The faster you go, the shorter the path becomes. You experience both effects simultaneously. Time slows down for you, and the universe ahead shrinks. The two phenomena ensure that every observer, regardless of their motion, agrees on one universal constant, the speed of light. This is the strange beauty of relativity. Space and time are not fixed backgrounds, but living dynamic entities that bend to preserve the cosmic rules. To us on Earth, the traveler's journey seems long and slow, stretched across decades. To the traveler, it's brief and compressed. Both perspectives are true, and both fit perfectly within the structure of space-time. There's no contradiction, because in relativity, reality depends on the observer's frame of reference. What's even more mind-bending is that this contraction isn't something the traveler would consciously feel. Inside their ship, everything appears normal. The walls, the instruments, the seats, all are unchanged because everything inside the same frame of motion contracts equally. There's no sense of squeezing or distortion within the ship. But from the perspective of an outside observer, the ship itself appears shortened along the direction of travel. This shortening isn't an optical illusion or a visual trick. It's a geometric reality written into the equations of space-time. To understand why this happens, think back to how relativity keeps the speed of light constant. If light's speed can never change, then when motion affects time, it must also affect space to compensate. As a traveler moves faster, the light that bounces inside their ship, say between two mirrors, must still travel at the same universal speed. For that to remain true, the distances the light covers inside the ship must shrink as seen from outside, and the passage of time must slow. This perfect balance ensures that no matter how fast anyone moves, the speed of light always remains constant, a kind of cosmic equilibrium that space-time maintains with infinite precision. On an emotional level, this concept is staggering. It means that distance, something we think of as fixed and immovable, is not absolute at all. What looks like an unreachable stretch of the universe to one observer can become traversable to another, moving at extreme speeds. Relativity doesn't just bend space and time. It binds them together, ensuring that one cannot change without the other. And here's where the wonder deepens. This contraction of space and dilation of time aren't separate curiosities. They are the universe's way of maintaining consistency. Without them, the cosmos would break its own rules. If time didn't slow and space didn't contract for fast-moving objects, different observers would measure different speeds for light, and the entire foundation of relativity would collapse. Instead, the universe elegantly reshapes itself around motion, flexing space and stretching time so that the laws of physics remain true for everyone, everywhere. To see this in action, think of high-energy particles called muons, created in Earth's atmosphere by cosmic rays. These muons have a very short lifetime, so short that, by classical physics, they shouldn't be able to reach the surface of the Earth before decaying. Yet they do. The reason? From our perspective, their internal clocks are ticking slower, time dilation at work. But from the muon's perspective, the distance through Earth's atmosphere has contracted, length contraction at work. Each view is valid in its own frame, and both lead to the same observable outcome. The particles reach the surface precisely because space and time reshape themselves depending on motion. This interplay between time dilation and length contraction is more than just a curiosity of high-speed travel. It's a fundamental expression of how reality works. It tells us that space and time are not separate stages, but components of a single, malleable fabric, space-time, that bends, stretches, and reshapes itself to preserve the cosmic order. The faster we move, the more that fabric adjusts, folding the universe tighter and tightening time's flow. So, for a traveler nearing light speed, space no longer feels infinite. The stars ahead draw closer, their distances collapsing into manageable stretches. What was once unreachable becomes reachable, not because the traveler is breaking the laws of physics, but because the laws themselves adapt to motion. It's a profound, humbling reminder that our perception of the universe, the way we define distance, time, and reality, is inseparable from how we move through it. And if space can shrink and time can stretch depending on motion, one might ask, why is it that light can move so freely, so effortlessly, without ever slowing or bending to these constraints? The answer lies in the nature of light itself, in the fact that photons have no mass and therefore play by a different set of rules. They are not bound by time as we are. They do not experience motion as we understand it. For them, the journey from one end of the cosmos to another happens in no time at all. Understanding why light can travel this way reveals something fundamental about what makes it special, and why it alone can move at the ultimate cosmic speed. Light occupies a special place in the universe. It doesn't obey the same rules that govern matter. It transcends them. Unlike anything that has mass, light doesn't need to accelerate to reach the cosmic speed limit. It's not trying to catch up to C. It's already there, eternally, effortlessly. A photon, the smallest possible packet of light, is born moving at light speed, and it remains that way for its entire existence. This is not a feat of propulsion or energy. It's simply the nature of what light is. To understand why, we have to look at the one defining characteristic that sets photons apart from all matter. They have no rest mass. Everything we're familiar with, atoms, planets, people, stars, has mass, and that mass resists acceleration. The greater the mass, the more energy you need to make it move faster. This resistance is what prevents massive objects from ever reaching light speed. But photons exist outside this restriction entirely. Their rest mass is zero, which means that if you were to somehow imagine them at rest, they wouldn't exist in that state at all. For light, standing still is physically meaningless. It's simply not an option in the universe's design. This is a subtle but profound idea. For something that has mass, motion through space-time involves both space and time components. You move through time as you move through space, and the balance between the two changes with your velocity. But for something with zero mass, like light, the balance shifts completely. A photon moves entirely through space and not at all through time. From its own perspective, if we could somehow assign one to it, there is no passage of time between the moment it is emitted and the moment it is absorbed. Whether it's crossing your room from a lamp or spanning billions of light years from a distant galaxy, for the photon itself, the journey takes no time at all. To us, that light might travel for eons. To the photon, it happens instantly. This timelessness is not poetic exaggeration. It's a direct consequence of relativity. Time dilation increases as you move faster, and for something traveling at the speed of light, time dilation becomes infinite. That means time effectively stops for the photon. Likewise, length contraction, the phenomenon where space shortens in the direction of motion, becomes absolute for light. From the photon's point of view, the entire universe collapses into a single, infinitesimally thin sheet, with its point of emission and its destination effectively touching. The photon doesn't cross space in the way we think of motion. It's more accurate to say that space itself connects its origin and destination directly. This is why photons require no energy to maintain their speed, because they're not accelerating through space-time in the way we do. They exist in a state where their velocity is always c, the speed of light in a vacuum, the same constant that defines the structure of space-time itself. The equations of relativity show that for any massless particle, motion at c isn't just allowed, it's mandatory. There is no slower option. The laws of physics don't give photons a choice. To put it another way, if the universe is a vast stage of space and time, then everything with mass is forced to move across that stage at different paces, balancing motion through space with motion through time. But photons, the actors made of pure energy, don't move across the stage. They are the spotlight itself, illuminating the entire scene in one instantaneous act. And this characteristic has deep implications for how the universe works. Because photons are massless, they also carry information about the fundamental structure of space-time. They reveal the geometry of the universe simply by existing. Their constant speed isn't something imposed externally. It's a direct reflection of how reality is built. The speed of light, c, is not just the maximum speed allowed. It's a property of spacetime itself, the rate at which space and time exchange energy and information. Light, in a sense, rides the curvature of spacetime perfectly. It's worth pausing to think about how alien this is to our everyday experience. Everything we interact with, from cars and planes to atoms and molecules, requires energy to move. Everything experiences time. Everything occupies space. But light isn't bound by those same relationships. It's neither at rest nor in motion as we understand it. It's in a state of eternal, unchanging speed. When you turn on a flashlight, the photons that leave it don't accelerate outward. They appear already traveling at c. Even the processes that create them, say the vibration of an atom or the transition of an electron, release photons that instantly emerge at full cosmic speed. This is also why light interacts with time and space so elegantly. When photons pass through different mediums, air, glass, water, their effective speed appears to change, but in truth, they are not slowing down in the vacuum between atoms. Instead, they are absorbed and re-emitted by the material's particles, creating the illusion of reduced speed. In empty space, nothing can interfere with them. There's no friction, no drag, no resistance. They simply glide along spacetime at the one speed reality permits for massless energy. Photons also carry no sense of aging. The light that left a distant galaxy billions of years ago has not felt that passage of time. For us, that light has been traveling for eons, crossing the expanding fabric of the cosmos to reach our telescopes. But for the photons themselves, the emission and the arrival are the same event. They have no before and after, no experience of duration. That's why astronomers often refer to light as a kind of cosmic messenger, a particle that transcends the normal flow of time to bring us information from the farthest corners of the universe. This property, being born at light speed, existing outside the flow of time, makes light the perfect embodiment of Einstein's space-time geometry. Light doesn't defy the laws of physics, it defines them. The speed of light, c, isn't just a number describing how fast photons move. It's the very scaffolding upon which the universe is constructed. It's the built-in relationship between distance and duration, the rule that ensures causality and order. And perhaps the most poetic truth of all is this: everything we see, every sunrise and star, every shimmer of reflection, and every shadow, is light revealing the universe's own structure. Every photon we observe is a traveler that has never known the passage of time, a messenger that exists only to connect moments of energy across the vastness of space. But to truly appreciate what this means, we need to look deeper at the thing light travels through, the medium that gives meaning to its speed and shape. Because light doesn't just move across an empty void. It moves through something profound and dynamic, space-time itself. And space-time isn't just a passive stage where matter and energy perform. It's an active participant, a living geometry that determines how everything in the universe moves and interacts. Space-time, the very fabric of reality, is not a stage, not a passive backdrop on which the drama of the universe unfolds. It is, in every sense, an actor itself, an active, dynamic framework that shapes everything within it. For centuries, scientists imagined space as empty and time as separate, two independent arenas where matter and energy played out their roles. But Einstein shattered that illusion. He showed that space and time are fused into a single, flexible entity called spacetime, and that this fabric doesn't just host events, it dictates how those events occur. Everything, every particle, every planet, every galaxy, moves according to the shape of spacetime. And that shape, in turn, is determined by the matter and energy within it. This means the universe is not like a stage upon which actors perform. It's like a living, breathing field that bends, twists, and flows with the presence of energy. When you move through space-time, you're not gliding across an empty void. You're following the curves and contours of an invisible geometry that defines what's possible and what's not. In this geometry, the speed of light isn't just fast, it's fundamental. It's not a random number that happens to cap how quickly things can move. It's a built-in feature of the structure itself, the ultimate conversion rate between space and time. When we say that nothing can move faster than light, we're not talking about a physical speed limit like a sign on a cosmic highway. We're talking about the shape of reality itself. Moving faster than light would mean cutting across space-time in a way that space-time doesn't allow. It's not that you're being stopped by resistance, it's that there's simply no path for such motion to exist. You can think of space-time as a kind of four-dimensional landscape where all objects follow specific routes, what physicists call world lines. These world lines trace each object's motion through space and time. For anything with mass, those world lines always stay within the boundaries set by light's trajectory. The paths of light itself, those perfect 45-degree lines in the space-time diagram, mark the edge of what's possible. Nothing with mass can ever tilt its path beyond that boundary, because doing so would mean moving outside the very geometry that defines the universe. Imagine space-time as a massive, unbreakable web stretched across reality. Light travels along the tightest possible threads in that web, the ones that define its tension and pattern. You, me, and every object with mass move across thicker, slower threads woven beneath those. The web allows us to move faster or slower depending on how much energy we put in. But there's one thread, the one traced by light, that marks the absolute limit. To move faster than that wouldn't just mean breaking the rules. It would mean leaving the web altogether, stepping out of existence as we know it. The profound truth is that space-time determines how energy and matter behave, not the other way around. Its curvature tells matter how to move, and matter tells space-time how to curve. This was Einstein's crowning insight, the idea that gravity itself isn't a force pulling on objects, but the result of this curvature. When you throw a ball or watch a planet orbit a star, what you're really seeing is motion along the curved paths that space-time prescribes. The same structure that defines those orbits also defines the speed of light. It's all part of one grand, interlocking system. So when we say that the universe has a speed limit, we're really saying that space-time has a specific geometry, one that locks together space and time in such a way that c naturally emerges as the ratio between them. You can move through space faster or slower, but to do so changes how you move through time. The speed of light represents the perfect balance point between those two motions, the slope of the fabric itself. It's not something to be surpassed, because it's not a speed through space in the traditional sense. It's the very shape of how space and time are connected. This is why photons, those massless messengers of light, always travel at that speed. They aren't fighting against a limit, they define it. They move along the natural curves of space-time itself, following the geometry perfectly, without any resistance or deviation. Everything else, every planet, particle, and person, is bound within that geometry, forever moving at slower rates because our mass prevents us from following the same kind of path. Think of it this way. Space-time is like a cosmic river. Light doesn't swim through it. It is the current. Everything else floats within it, moving according to how the flow bends and stretches. To go faster than light would mean moving against the current in a way the river simply doesn't permit. The universe doesn't have the mathematical room for such motion to exist. This perspective changes everything about how we view the cosmos. The speed of light isn't a limit that frustrates us. It's a revelation of the universe's inner logic. It tells us that the cosmos isn't chaotic, but deeply ordered, built from principles that keep everything coherent and consistent. Spacetime ensures that cause always precedes effect, that energy and momentum are conserved, and that every observer, no matter where or how fast they move, experiences a universe that plays by the same fundamental rules. In essence, space-time is the law of nature embodied, the silent framework that ensures that light, gravity, matter, and time all move in concert. It's not just the place where things happen, it's what makes things happen. The speed of light isn't a ceiling we can one day break through. It's the very shape of the universe's foundation. To exist at all is to live within that shape, to be bound by it, guided by it, and made possible because of it. And that brings us to one of the most elegant consequences of this structure, the preservation of causality, the order of cause and effect that underpins reality itself. Without the light speed limit, the universe's logical consistency would collapse. Events could occur before their causes, messages could arrive before they were sent, and time itself would lose all meaning. But because of space-time's immutable geometry, that never happens. Light speed doesn't just shape motion, it preserves reason itself in the cosmic order. Causality, the idea that every effect must follow its cause, is one of the most sacred principles in all of physics. It's so deeply embedded in our understanding of reality that we rarely stop to question it. You flip a switch and a light turns on. You drop a stone and it falls. Every event we witness unfolds in a logical, sequential order. Something happens because something else made it happen. It's the rhythm of existence, the forward flow of time that gives meaning to cause and consequence. But this elegant order depends on one crucial cosmic rule: nothing can carry information faster than light. This limit, the same C that defines the structure of space-time, acts as the guardian of causality, ensuring that no event in the universe can influence another before it's supposed to. It keeps time moving in one direction, from past to future, preserving the logical consistency of reality. If that limit didn't exist, if matter or information could somehow outrun light, then the very structure of cause and effect would crumble. To understand why, imagine two observers, one on Earth and another traveling on a spaceship moving close to light speed. According to relativity, each observer experiences space and time differently. Events that seem simultaneous to one might not be simultaneous to the other. This isn't a matter of perception, it's how the universe actually works. The faster you move, the more the slices of space-time, the what's happening now moments, tilt relative to other observers. Einstein called this the relativity of simultaneity, and it's one of the most profound insights in physics. Now, as long as all communication between these two observers stays below or equal to the speed of light, causality remains intact. The order of events might differ slightly depending on who's watching, but no one will ever see an effect occur before its cause. However, if it were somehow possible to send a message faster than light, that delicate structure would collapse instantly. From one frame of reference, the message might be sent before an event occurs, while in another frame, it might be received before it was sent. That means, depending on your point of view, you could literally witness an effect precede its cause. This isn't just a quirky side effect of relativity, it's a fundamental contradiction. It means you could, in principle, warn someone about something before it happens, or even prevent it entirely, creating the ultimate paradox. Physicists call these closed time-like loops, situations where information travels in a circle through time, looping back to alter the very event that created it. That's where the nightmare of causality truly begins. A universe where logic eats itself. Take a simple example. Suppose you could send a signal faster than light, say, from your ship to Earth. In one frame of reference, that signal might appear instantaneous. But in another, due to the way relativity warps the ordering of time, the signal might actually arrive before you sent it. Someone on Earth could then reply with their own faster-than-light message, sending it back to you before you even decided to transmit the first one. The result? You'd receive their response to a message you haven't yet sent. It's not science fiction. It's a mathematical consequence of exceeding light speed. The universe's logic breaks down. And when logic breaks, reality itself follows. If information can arrive before it's sent, then events no longer have a coherent order. You could see something before it's caused, like an explosion before the detonation, or hear a word before it's spoken. Even worse, you could theoretically change the cause after seeing the effect, unraveling the entire concept of time as a linear progression. In that kind of universe, prediction, memory, and history would become meaningless. There would be no true past or future, only a tangled web of contradictions. This is why the light speed limit isn't just a rule about motion, it's a rule about logic. It's what ensures that the universe makes sense. It keeps every observer's experience of reality internally consistent, even if their perspectives differ. Within the bounds of C, events might appear to shift in order depending on where you are and how fast you're moving, but all observers will agree on one fundamental thing. No effect ever occurs before its cause. And this constraint is not just theoretical. In every experiment, every test of relativity, causality remains perfectly preserved. Information always travels slower than or at the speed of light. Even the most exotic phenomena we know, from quantum entanglement to black hole radiation, obey this rule. It's as if the universe itself enforces it, refusing to let reality unravel. In fact, you can think of c as the speed at which information moves through space-time. Whether that information is carried by light, gravity, or any other force, it cannot propagate faster than this cosmic constant. That's why we can't feel what happens on the sun instantly. We only know about it 8 minutes later, when the light and information finally reaches us. The same goes for distant stars, galaxies, and even the gravitational ripples from colliding black holes. All arrive at precisely the same maximum rate allowed by the geometry of space-time. It's almost poetic. Light, the very thing that illuminates the universe, also defines its logic. It sets the pace not just for motion, but for cause and effect, ensuring that every heartbeat, every thought, every event follows a coherent sequence. Without that boundary, we'd live in a chaos where time could loop backward, where effects could undo causes, where the universe could contradict itself. So when we talk about the speed of light as the universal limit, we're really talking about the limit that protects reason itself. It's the universe's built-in firewall against paradox. It ensures that the cosmos runs on a consistent script, where actions lead to reactions, where signals move forward through time, and where reality unfolds in a way that can be understood, predicted, and trusted. And yet, this very rule, this safeguard of cosmic logic, invites us to imagine the impossible. What would happen if something could exceed that speed? What would it mean for a universe bound by causality if something or someone could break free of it? The thought itself leads to some of the strangest ideas in theoretical physics. Tachyons, warp drives, and time travel paradoxes that seem to tease the edges of reason. But each of these thought experiments, in the end, brings us back to the same profound conclusion. The light speed limit is not a prison. It's the stitching that holds reality together. What if, somehow, you could break the limit? What if the cosmic rule that binds every star, particle and signal could be bent or shattered. It's a question that has haunted physicists, philosophers, and dreamers alike for more than a century. What if something could travel faster than light? What would it mean for a universe built on cause and effect, on the steady unfolding of time? Could we send messages across galaxies in an instant? Could we visit distant stars, or even travel back into our own past? At first glance, it's an intoxicating thought. The idea of outrunning light, escaping the long delays of space and time, transcending the cosmic speed limit that keeps us confined to our little corner of the Milky Way. Science fiction is full of this desire. Warp drives, hyperspace, wormholes, all attempts to imagine what breaking the light speed barrier might feel like. But when you look deeper, when you follow the mathematics and the logic of relativity to their conclusions, you realize that such a feat wouldn't just challenge the laws of physics, it would unravel them. Let's begin with the simplest possibility. Imagine a hypothetical particle that could always move faster than light. Physicists have a name for such a thing: tachyons, from the Greek word tachys, meaning swift. Tachyons are purely theoretical. No one has ever observed one, and many doubt they could exist at all. But in the equations of relativity, they have a strange and troubling property. Because they would always travel faster than light, their relationship with time would be reversed. The faster a tachyon moved, the less energy it would need. In fact, as its energy decreased, its speed would increase, the complete opposite of what happens with normal matter. And the truly bizarre part? For some observers, a tachyon's motion would appear backward in time. That means if tachyons existed, they could, in theory, send information from the future to the past. You could receive a message before it was sent. You could watch an event's outcome before its cause even occurred. And with a bit of clever manipulation, you could construct what physicists call causal loops, situations where information circles endlessly through time. Imagine sending yourself a warning from the future, or receiving knowledge of an event that hasn't happened yet. The paradoxes pile up quickly. What if that warning changed your actions, preventing the event from ever occurring? What happens to the message then? This is the infamous grandfather paradox, the logical nightmare where changing the past erases the reason for the change itself. This isn't just a problem for time travel stories. It's a real, unavoidable consequence of faster-than-light motion in a relativistic universe. If you can exceed c, then depending on your frame of reference, effects can precede causes. One observer's after becomes another's before. The structure of spacetime doesn't forbid this mathematically, but it destroys causality in the process. It turns reality into a tangled mess of contradictions, where the universe can't agree on the order of events. But even if we set tachyons aside, what about the more popular ideas? Warp drives and wormholes. These are staples of science fiction, and even subjects of serious theoretical research. The concept of a warp drive, such as the Alcubierre drive, proposed in the 1990s, doesn't involve moving an object faster than light through space. Instead, it imagines bending space itself, compressing it in front of a spacecraft and expanding it behind. The ship would sit in a bubble of space-time that rides the distortion, moving faster than light relative to outside observers, without locally breaking the speed limit. It sounds brilliant, and mathematically it might even be possible, but the catch is enormous. Such a drive would require negative energy density, a kind of exotic matter with properties opposite to normal energy. It would bend space-time in ways that defy all known physics, demanding more energy than exists in the observable universe. Even worse, many solutions that allow for superluminal travel also allow for closed time-like curves. Essentially, time loops where an object or signal can return to its own past. In other words, warp drives and wormholes aren't just faster-than-light shortcuts. They're potential time machines, complete with all the paradoxes that come with them. This is where relativity flexes its power. Einstein's equations are extraordinarily flexible. They allow for all sorts of strange geometries, including wormholes and warped regions of space-time. But nature itself seems to resist them. The ingredients needed, negative energy, exotic matter, perfect symmetry, don't seem to exist in the quantities required. It's as if the universe permits these ideas on paper, but prevents them in practice. The mathematics teases the possibility, but reality enforces the rule. Even quantum mechanics, with all its strangeness, refuses to break the light-speed barrier. Quantum entanglement, for instance, might seem to transmit effects instantaneously between distant particles, but no usable information actually travels faster than light. The correlation between entangled particles only makes sense when compared afterward, after light-speed communication has occurred. It's as though the universe allows us to flirt with the illusion of faster-than-light effects, but always keeps causality safe behind a veil of mystery. The lesson here is profound. The light-speed limit isn't just a technical constraint. It's the safeguard of reality. It's what keeps the universe consistent, coherent, and logical. If it were possible to move faster than light, then everything we know about order, time, and information would collapse. The flow of history would become a chaos of feedback loops and contradictions. There would be no stable now, no trustworthy before or after. You could, theoretically, watch your own birth before your parents met, or see a star explode before it was ever formed. Einstein once remarked that the distinction between past, present, and future is only a stubbornly persistent illusion. But even that illusion depends on the light speed limit to hold it together. It's what keeps the arrow of time pointing forward, ensuring that memory precedes action, that signals move outward from their sources, and that the universe evolves in an orderly way. So the next time you look at the night sky and think about the unreachable distances between stars, remember, that limit isn't a cruel barrier. It's a gift. It's what makes reality possible. Without it, everything would fall apart. Space and time would lose their meaning, cause and effect would dissolve, and the universe itself would unravel into paradox. The light speed limit is the invisible guardian of cosmic order, the rule that ensures existence has a rhythm, a flow, and a logic that can be understood. But even as this rule stands unbroken, there are still mysteries that test its edges. One of them comes from the strange quantum world, a realm where particles seem to influence one another instantaneously, across any distance. It's a phenomenon so puzzling that Einstein himself called it spooky action at a distance. It's called quantum entanglement, and at first glance, it appears to challenge the very speed limit that keeps the universe sane. Quantum entanglement, a phenomenon so strange, so deeply counterintuitive, that even Einstein himself couldn't accept it fully. He famously called it spooky action at a distance, because it seemed to suggest something impossible, that two particles, separated by vast distances, could somehow affect each other instantaneously, as if they were communicating faster than light. To this day, entanglement remains one of the most mysterious and misunderstood concepts in all of physics, a riddle that seems to mock our understanding of space, time, and the cosmic speed limit. Here's how it works, at least in simplified form. When two particles, say photons or electrons, become entangled, their physical states become linked in such a way that they can no longer be described independently. They share a single, unified quantum state, even when separated by light years. If you measure one particle and find it spinning up, the other will instantly be found spinning down. It doesn't matter how far apart they are, the connection appears to be instantaneous, defying distance and time. At first glance, this seems to outright violate relativity. After all, if the particles are billions of kilometers apart, and one seems to know what happens to the other instantly, doesn't that mean information has traveled faster than light? Wouldn't that mean that the universe's most sacred rule, the limit set by c, has been broken? That's exactly what Einstein thought when he, along with Boris Podolsky and Nathan Rosen, published their famous 1935 paper, the EPR paradox. They argued that quantum mechanics must be incomplete because it seemed to allow this kind of faster-than-light influence. Einstein believed that there had to be some hidden variables, unseen factors that determined the outcomes of these measurements locally, keeping everything within the boundaries of relativity. To him, the idea that the universe could allow instantaneous effects across distance was intolerable. But the decades that followed revealed something astonishing. Einstein's skepticism, while understandable, was misplaced. Experiments performed in the 1960s by physicist John Bell, and later refined with extraordinary precision by Alain Aspect and others in the 1980s and beyond, proved that quantum entanglement is real, not an illusion, not a trick of measurement, but a fundamental property of nature. The results consistently showed that no local hidden variables could explain the correlations between entangled particles. In other words, nature really does behave in this non-local way. However, and this is the crucial point, entanglement does not actually allow for communication or the transfer of information faster than light. The key lies in the subtle but profound nature of quantum mechanics. When you measure one of the entangled particles, its state becomes definite, and the other particle's state becomes definite too. But the result of that measurement, whether up or down, horizontal or vertical, is random. You can't control what outcome you get. And since you can't control it, you can't use it to send a meaningful signal to someone else. Imagine two people, Alice and Bob, who share a pair of entangled particles. Alice keeps one, and Bob takes the other to a distant planet. When Alice measures her particle, she gets a random result, maybe spin up. Instantly, Bob's particle will have the opposite spin down. But from Bob's perspective, when he measures his particle, he also just gets a random result. Neither can predict or control the outcome, and neither can tell what the other has measured until they compare notes later through ordinary communication, which still requires light speed or slower signals. So while the correlation between their results is instantaneous, the information about those results is not. No data, no message, no usable signal has traveled faster than light. The universe's speed limit remains perfectly intact. What's happening here isn't a violation of relativity. It's a deeper expression of quantum reality, a realm where distance doesn't quite mean what we think it does, and where entangled systems behave as a single entity spread across space. You could say that entanglement doesn't send information through space at all. It transcends space. The two particles aren't communicating. They're sharing a single quantum existence. When one is measured, the state of the system as a whole becomes definite. There's no message sent, no signal transmitted, just a single reality expressing itself across two locations. It's as if the universe is reminding us that separation itself is partly an illusion, that what we perceive as two distant points might, at the quantum level, be facets of one deeper, connected whole. And yet, despite how weird this sounds, the framework of relativity remains untouched. All measurable information, all energy, all physical interactions, still obey the cosmic limit. Entanglement may make the universe feel eerily interconnected, but it doesn't let us break the rules. The universe, in its strange way, allows mystery and consistency to coexist. In a sense, quantum entanglement is a cosmic balancing act. It teases us with the appearance of instant connection, inviting us to imagine faster-than-light communication. Yet, Every time we try, the laws of physics gently but firmly refuse. It's as if nature is whispering, "You can glimpse the unity of things, but you can't exploit it to break me." This strange phenomenon also teaches us something profound about the universe's architecture. The light speed limit doesn't just govern the macroscopic world of rockets and radio waves. It governs the very fabric of information itself. The same constant c that defines how light moves through space also defines how causality and communication propagate through reality. Even in the most abstract realms of quantum mechanics, that rule endures. So while entanglement may seem like a loophole, it's not a rebellion, it's a revelation. It tells us that the universe is far more interconnected than we ever imagined, but still perfectly consistent with the cosmic geometry of space-time. The speed limit stands firm, not as a barrier to wonder, but as the rule that allows wonder to exist at all. And speaking of distances and limits, there's another phenomenon that seems, at first glance, to defy the same cosmic constraint, the expanding universe itself. Astronomers have discovered that distant galaxies appear to be moving away from us faster than light. How can that be? If nothing can travel faster than light, why do we see galaxies receding beyond that limit? The answer takes us to one of the grandest revelations of modern cosmology, the realization that it's not objects moving through space that exceed light speed, but space itself that's expanding, carrying everything with it. One of the most common questions people ask when they first learn that the universe is expanding is deceptively simple. If nothing can move faster than light, then how can distant galaxies be receding from us faster than light? Astronomers routinely talk about galaxies whose light has taken over 13 billion years to reach us. And some even say that those galaxies are moving away faster than at first glance. This sounds like a contradiction, as if the universe itself were breaking its own rule. But here's the crucial truth. Those galaxies aren't moving through space faster than light. Instead, it's space itself that's expanding. And relativity not only allows this, it requires it. To understand this, we have to rethink what we mean by motion. When we say that a car moves down a road or a planet orbits the sun, we're describing motion through space. An object changing its position relative to something else within a fixed background. But in cosmology, on the scale of the entire universe, that background, space-time, is not fixed. It's stretching, evolving, changing with time. Galaxies aren't racing through the cosmic fabric like ships cutting through water. They're more like raisins in a rising loaf of bread. As the dough expands, the raisins grow farther apart, even though they're not moving within the dough itself. The expansion of the bread creates the increasing distance between them. This analogy beautifully captures what's happening on the largest cosmic scales. Galaxies are mostly at rest relative to the expanding fabric of space-time around them. It's not that they're speeding through the universe, it's that the universe is expanding between them. Space itself is stretching, and with that stretching comes an increase in the measured distance between galaxies. The farther apart two galaxies are, the more space there is between them, and the faster that space expands. So far enough away, the expansion can carry galaxies apart faster than light without violating relativity in the slightest. That's because Einstein's speed limit applies locally to objects moving through space, not to the expansion of space itself. The fabric of space-time has no material substance. It's not made of stuff that moves in the traditional sense. It can expand, contract, or curve, and nothing in the laws of relativity forbids that. In fact, relativity provides the equations that describe exactly how it happens. The famous Friedmann-Lemaitre equations derived from Einstein's general theory of relativity. These equations show that space-time can grow or shrink depending on the density and energy of the universe. You can even picture the expansion more precisely using the idea of cosmological redshift. When light travels across expanding space, the very fabric it moves through stretches. The wavelength of that light gets stretched too, making it redder by the time it reaches us. The farther away a galaxy is, the more its light has stretched. Not because it's moving rapidly through space, but because the space between us and it has expanded during the light's journey. This stretching of light is direct evidence that the universe's expansion is not a movement through space. It's the stretching of space itself. This concept is central to modern cosmology and helps us understand phenomena like the cosmic horizon. The cosmic horizon marks the farthest distance from which light has had time to reach us since the beginning of the universe. Beyond that horizon, galaxies are receding so rapidly, carried by the expansion of space, that their light can never reach us, no matter how long we wait. It's not that they're moving faster than light through space. It's that the space between us and them is expanding so quickly that any light they emit gets swept away faster than it can travel. In essence, these galaxies are beyond our causal reach. They exist, but their signals can never influence us. It's also important to note that the universe's expansion is not uniform everywhere. On small scales, within galaxies, star systems, and even galaxy clusters, gravity dominates. It holds matter together tightly enough that local space doesn't expand. The Milky Way isn't growing larger, nor is our solar system. The space between you and your chair isn't stretching. Expansion only becomes significant over immense cosmic distances, where the gravitational binding between structures is too weak to resist the universe's overall growth. What's even more fascinating is that this expansion is not slowing down as early astronomers once expected. In the late 1990s, scientists studying distant supernovae discovered that the universe's expansion is accelerating, driven by a mysterious, repulsive energy we now call dark energy. This discovery was one of the greatest surprises in modern science. It means that not only is space expanding, but it's doing so at an ever-increasing rate, stretching galaxies farther and faster apart as time goes on. Over billions of years, more and more galaxies will cross beyond our observable horizon, disappearing forever from view, their light redshifted into darkness. But none of this, not even galaxies receding faster than light, nor the accelerating expansion of space, violates Einstein's speed limit, because that limit applies to motion within spacetime, not to the evolution of spacetime itself. The light speed rule defines the structure of spacetime, and expansion happens according to that structure. Space doesn't need to move through anything to grow. It simply redefines distance. It's as if the universe is constantly redrawing its own map. So when we look at distant galaxies and say they're moving away faster than light, what we really mean is that the distance between us and them is increasing faster than light could traverse it, not because they're outrunning light, but because the metric that defines distance is itself stretching. In this way, relativity elegantly allows a universe that grows, evolves, and even accelerates without ever breaking its own fundamental rule. It's a subtle distinction, but a profound one. The cosmic speed limit stands firm even in a universe where space itself is expanding faster than light could cross it. That's the genius of relativity. It doesn't just describe motion, it describes reality itself. And within that reality, the speed of light plays yet another, even deeper role, not just as a limit or a constant, but as a kind of cosmic conversion factor. It links space, time, energy, and mass together into one unified whole. The number c doesn't merely cap how fast things move, it defines how everything in the universe relates to everything else. The universe may appear vast, mysterious, and filled with chaos. Stars exploding, galaxies colliding, particles popping in and out of existence. But underneath that apparent disorder lies an extraordinary truth. The cosmos is consistent. It follows precise mathematical laws that hold true everywhere and everywhen. Gravity behaves the same way in Andromeda as it does on Earth. Light bends around stars exactly as Einstein's equations predict. Energy is conserved. Motion is predictable. Every atom, every field, every galaxy obeys the same rules. And at the heart of all this consistency, the principle that makes the laws of nature work at all, lies the universal speed limit, the speed of light. Without this limit, everything we know about physics would collapse. The equations that govern energy, momentum, electromagnetism, and gravity would lose coherence. The very idea of before and after would break down. Cause and effect, the backbone of logic, of science, of existence itself, would dissolve into contradiction. The speed of light isn't just a number, it's the rule that ensures the universe makes sense. It's the keystone of reality. Imagine a world without a universal speed limit. Information could travel instantaneously or even backwards in time. You could send a message to the past, perhaps warn yourself of a mistake before it happens, or alter an event that already occurred. But that's not just paradoxical, it's physically destructive. If cause and effect can reverse, then the chain of consequences that keeps the universe ordered unravels. Energy conservation laws would fail. Systems could create or destroy energy without limit. The predictable harmony that allows galaxies to form, atoms to hold together, and life to evolve would vanish in an instant. This isn't just philosophical speculation, it's mathematical fact. Relativity, quantum field theory, thermodynamics, electromagnetism, all of them are built on the assumption that there's a maximum rate at which information and influence can propagate, c. It's what keeps events ordered in time, prevents infinite feedback loops, and ensures that physical processes are local, that one region of space can only affect another through measurable, causal means. Consider a simple electromagnetic field. When a charge moves, it produces changes in the electric and magnetic fields around it. Those changes ripple outward at the speed of light. This delay is crucial. It's what allows us to calculate radiation, energy transfer, and the behavior of light itself. If those field changes could propagate instantaneously, energy could appear anywhere at any moment, with no physical mechanism connecting cause and effect. It would break Maxwell's equations, the foundation of electromagnetism. Or take Einstein's famous equation that links mass and energy. Energy equals mass multiplied by the square of the speed of light. That c squared isn't decorative. It's the conversion factor that unites two seemingly different forms of existence into one. If c weren't constant, or if there were no limit at all, the relationship between matter and energy would lose meaning. A small amount of mass could release infinite energy, and the stability of matter, of stars, of planets, of you, would vanish. Even the structure of spacetime itself would become meaningless. In relativity, c defines how space and time transform between observers moving at different velocities. Without a fixed speed limit, those transformations wouldn't hold together. Observers could disagree not only on durations and distances, but on the very order of events. Two people might witness entirely contradictory universes, one in which event A causes event B, and another in which event B causes event A. Without C, there would be no shared reality. This universal consistency is what allows physics to exist as a science at all. The light speed limit gives us predictability. It ensures that if we perform an experiment here on Earth, its results would hold true on the other side of the galaxy. It's what lets GPS satellites calculate positions, what lets energy balance in every equation, what makes the motion of planets, photons, and particles intelligible. C isn't just a cosmic boundary, it's the bridge connecting all physical laws. In a way, the light speed limit is the universe's internal logic, the rule that keeps contradictions at bay. Think of reality as a vast network of causes and effects, a web that stretches across space and time. The speed of light defines the strength and spacing of that web. Each event can only influence others within a certain boundary, called its light cone. Anything outside that cone, too far away or too early in time, cannot be affected, no matter what. This simple geometric rule is what prevents chaos. It means that events unfold in an orderly, hierarchical fashion. It's what keeps the universe from becoming an infinite tangle of overlapping effects. And relativity doesn't just allow this order, it demands it. The structure of space-time itself is built to preserve causality. When you draw a space-time diagram with time running upward and space running horizontally, light always moves along diagonal lines, the edges of the light cone. Those diagonals are fixed. No matter how fast you go or where you are, your motion must always remain inside that cone. It's nature's way of saying, here is what's possible. Everything beyond this is forbidden. This consistency is also why our technological world functions. When we rely on signals from satellites, or synchronize clocks across continents, or beam data across optical fibers, we are literally working within the framework defined by CE. Even the smallest deviation from that limit would send shockwaves through every calculation. Without it, relativity wouldn't describe motion, quantum mechanics wouldn't predict outcomes, and the entire mathematical structure of physics, the grand tapestry of natural law, would tear apart. The light speed limit is not a restriction we fight against. It's the foundation that allows reality to be coherent. It keeps the universe from dissolving into paradox, preserves energy, and makes sure that everything, from the birth of a photon to the orbit of a planet, follows the same universal script. It's what allows us to ask questions and get meaningful answers, to predict, to measure, to understand. So when we look at that humble letter C in equations, just a small constant, 299,792 kilometers per second, we should see it for what it truly is, the anchor of existence. It's the heartbeat of the cosmos, setting the tempo for the dance of energy and matter. It's the reason the stars burn steadily, the reason time flows forward, and the reason reality itself doesn't collapse into contradiction. And this brings us to a more grounded revelation, the fact that these abstract ideas, born from deep thought and mathematics, don't just exist in theory. They affect our daily lives, shaping the technology we depend on. You've already experienced relativity, whether you've realized it or not. It's hidden in the signals guiding airplanes, in your phone's navigation system, in the way we communicate across the planet. The universal speed limit doesn't just keep physics consistent, it keeps modern civilization running. If you've ever used your smartphone to find the nearest coffee shop, tracked a flight, or navigated across a city using Google Maps, you've relied, without realizing it, on Einstein's theory of relativity. The Global Positioning System, GPS, is one of the most astonishing real-world applications of physics ever created, and it works only because we account for the strange, beautiful distortions of time and space predicted by relativity. Without Einstein's insights, your GPS would fail catastrophically, within minutes. Let's break down why. The GPS network consists of more than 30 satellites orbiting about 20,000 kilometers above Earth. Each of these satellites carries incredibly precise atomic clocks that measure time down to billionths of a second. They constantly broadcast timing signals toward the surface, and your phone or GPS receiver triangulates its position by comparing how long those signals take to arrive from several satellites at once. The system depends entirely on accurate timekeeping. Even a difference of 1 microsecond, 1/1,000,000th of a second, would translate into hundreds of meters of error in your calculated location. Now, here's where relativity enters the picture. According to Einstein's special relativity, time slows down for objects moving at high speeds compared to those at rest. The GPS satellites orbit Earth at roughly 14,000 kilometers per hour, so their onboard clocks tick slightly slower than identical clocks on the ground. This effect, called time dilation, makes the satellite clocks fall behind Earth-based clocks by about 7 microseconds per day. But that's not the only relativistic effect at play. Einstein's general theory of relativity, which describes how gravity warps spacetime, predicts something else. Time runs faster in weaker gravitational fields. Because GPS satellites orbit far above Earth's surface, where gravity is weaker, their clocks actually tick faster than clocks on Earth by about 45 microseconds per day. Now we have two competing effects. Special relativity slows the satellite clocks by 7 microseconds per day, while general relativity speeds them up by 45. Combine them, and the result is a net difference of about 38 microseconds per day. That might sound tiny, but in the world of GPS, it's massive. If engineers ignored that difference, the system's timing would drift by tens of nanoseconds every second, causing positional errors that accumulate rapidly. After just one day, your GPS would be off by about 10 kilometers. After a week, it would be completely useless. The map on your phone wouldn't just put you on the wrong street, it might put you in the wrong city. To prevent this, GPS engineers pre-correct the satellite clocks before launch. The atomic clocks on each satellite are tuned to tick slightly slower on the ground, so that once they're in orbit and affected by both gravitational and motion-based time dilation, they synchronize perfectly with clocks on Earth. The system also continuously recalibrates itself, accounting for tiny variations caused by orbital eccentricities, solar radiation, and even the subtle bending of spacetime by the Sun and Moon. This isn't a matter of fine-tuning theoretical physics, it's a daily necessity. Every position Fix Your Phone calculates, every ship navigating open oceans, every aircraft flight path, every self-driving car relies on relativity to work correctly. It's one of the most compelling proofs that Einstein's ideas weren't just abstract mathematics, they're woven into the fabric of modern life. And GPS isn't the only example. The same principles underpin other technologies we take for granted. The electromagnetic signals used for communications, satellite imaging, and even scientific measurements of Earth's shape must all be adjusted for relativistic effects. When scientists synchronize telescopes across continents to create planet-sized observatories, like the Event Horizon Telescope that imaged a black hole, they rely on relativity to coordinate data streams arriving at slightly different times. Even in particle accelerators like CERN's Large Hadron Collider, relativity is indispensable. As particles approach near-light speeds, their masses effectively increase and their clocks slow relative to the lab. Engineers must design the accelerators with these relativistic effects in mind, or the beams wouldn't stay stable. It's another reminder that relativity isn't an exotic concept reserved for cosmologists. It's a fundamental part of how our universe behaves, from the tiniest particles to orbiting satellites. It's almost poetic that something so cosmic, something born from Einstein's thought experiments about chasing light beams, has become so mundane, so practical, that billions of people use it every day without realizing it. The same equations that describe the bending of starlight around black holes also ensure your Uber driver finds you at the right corner. This is the quiet triumph of modern physics, the seamless marriage of the abstract and the everyday. Relativity connects the deepest structure of space-time to the smallest details of human experience. It governs not only how galaxies evolve, but how your phone keeps time. It proves that the universe's rules are not distant curiosities. They're the invisible scaffolding supporting our entire civilization. So, the next time your GPS calmly tells you to turn left in 200 meters, remember, that simple instruction depends on clocks ticking slower in orbit, on space-time bending around Earth, and on the speed of light itself remaining perfectly constant in the void between satellite and receiver. Every navigation app is a small celebration of Einstein's genius, an invisible tribute to the cosmic speed limit that makes both physics and your morning commute work. And yet, despite this astonishing precision and practicality, the idea of faster-than-light travel continues to capture the human imagination. Science fiction writers and dreamers have long imagined warp drives, hyperspace, and shortcuts through space-time. But while these ideas may be inspiring, they exist, at least for now, on the edge of speculation. In the real universe, the speed of light stands unbroken. The next step is to confront those dreams and myths directly. What does science say about them, and why do they remain, for the moment, only stories? The dream of faster-than-light travel has been one of humanity's most enduring fascinations. From starships in Star Trek leaping into warp, to spacecraft diving through wormholes in Interstellar, science fiction has taught generations to imagine the cosmos not as an unreachable expanse, but as a vast ocean waiting to be crossed. These stories fire our imagination because they offer freedom. Freedom from distance, from isolation, from the cosmic speed limit that seems to keep the stars forever out of reach. But while those visions make for incredible storytelling, the truth, as dictated by the physics of our universe, is far more sobering and perhaps even more awe-inspiring. To start, let's look at the idea of the warp drive, the crown jewel of faster-than-light fantasies. The most famous theoretical version was proposed in 1994 by Mexican physicist Miguel Alcubierre, inspired directly by Star Trek. In his paper, Alcubierre found a clever mathematical solution to Einstein's equations of general relativity that, in principle, would allow a spacecraft to move faster than light without actually breaking the cosmic speed limit. The trick? The ship itself would never move through space faster than light. Instead, it would sit inside a bubble of space-time. The bubble would compress space in front of it and expand space behind, effectively letting the ship surf a wave of warped space-time, carried along faster than light relative to distant observers. It sounds elegant, and it is. The equations themselves are internally consistent with relativity, meaning they don't break any mathematical laws. But there's a catch, a massive one. The Alcubierre drive requires something we've never observed and may not even be possible: negative energy density, sometimes called exotic matter. To create a warp bubble, you'd need energy that bends space-time in the opposite way of normal matter. Ordinary energy, like the kind in sunlight or nuclear reactions, curves space-time positively, attracting things toward it. Negative energy, on the other hand, would have the opposite effect. It would repel, stretching space-time outward. In theory, quantum mechanics allows for tiny fluctuations of negative energy in the vacuum of space. This is what powers phenomena like the Casimir effect, where two metal plates placed close together experience a measurable force due to vacuum fluctuations. But those effects are infinitesimally small. To build an Alcubierre warp drive large enough to move even a modest spacecraft, the amount of negative energy required would be astronomical, equivalent to the total mass energy of several suns. Some early estimates even suggested you'd need more energy than exists in the observable universe just to move a ship a few meters. Later refinements have reduced that number, but it's still absurdly beyond anything we could generate. Even if, somehow, we could harness negative energy, we'd face another serious problem: stability. The mathematics of warp bubbles suggests that the slightest disturbance could cause the bubble to collapse catastrophically, releasing its energy in a blast more powerful than a supernova. Moreover, inside the bubble, space-time would be so distorted that the crew might be completely isolated from the outside world, unable to control or even stop their motion once it began. It's a thrilling idea, but one that, at least for now, belongs firmly in the realm of imagination. Then there's the equally alluring idea of wormholes, tunnels through space-time that connect two distant points. The concept arose naturally from Einstein's equations in the early 20th century. A wormhole, in principle, could let you travel from one side of the galaxy to the other in seconds, without ever moving faster than light locally. Instead of flying across space, you'd simply take a shortcut through it. It's a beautiful concept, like folding a sheet of paper so that two distant dots touch, allowing a traveler to step instantly from one to the other. However, as with warp drives, the devil lies in the details. Wormholes, if they exist, would be incredibly unstable. Theoretical calculations show that any ordinary matter entering a wormhole would cause it to collapse instantly. To keep a wormhole open long enough for travel, you'd again need exotic matter with negative energy density to counteract the collapse. And even then, there's no guarantee it wouldn't snap shut or explode. We also have no observational evidence that naturally occurring wormholes exist, though some physicists speculate that they might exist at quantum scales, microscopic fleeting connections that appear and vanish within the foam-like texture of space-time itself. The notion of hyperspace, a separate dimension that allows one to jump across vast distances, is another creative invention of science fiction rather than a product of known physics. It works wonderfully as a narrative device, allowing heroes to cross galaxies in minutes, but it has no grounding in relativity or quantum field theory. In the real universe, there's no hidden dimension that lets you bypass the fabric of space-time. Everything, every particle, every beam of light, is bound within that fabric, moving at or below the cosmic limit defined by C. Even concepts like quantum tunneling, where particles appear to jump through barriers instantaneously, don't truly break the light speed rule. Tunneling is a probabilistic effect. It doesn't transmit usable information faster than light, and it's fully compatible with relativity. Time and again, the universe teases us with hints of shortcuts, only to reveal that its deeper structure still respects the same unyielding limit. It's tempting to believe that maybe, someday, technology will find a way to cheat these rules. After all, humanity has a history of turning impossibilities into realities. But the light speed limit isn't like the sound barrier, something that can be broken with enough thrust or clever engineering. It's not a technological problem, it's a geometric law of the universe. It's built into the structure of space-time itself. To surpass it would require rewriting the fundamental equations that describe reality, not just bending them, but creating a new universe where cause and effect, space and time, behave differently. So for now, faster-than-light travel remains a beautiful dream, one that fuels our imagination and pushes us to explore what's truly possible. And perhaps that's its greatest gift. It reminds us how vast, how mysterious, and how elegant the real universe already is. Even confined by the speed of light, we've sent probes beyond our solar system, seen galaxies billions of light years away, and detected ripples in space-time from merging black holes. The cosmic speed limit hasn't stopped us from reaching the stars in our minds. It's given us the challenge that defines exploration itself. And when we step back from those dreams and look at the bigger picture, we find something deeper still. That this universal speed limit, this unbreakable constant, reveals a profound order beneath the surface of existence. It's not merely a restriction. It's a sign of the universe's underlying harmony, the way energy, mass, and time interconnect. The fact that there is a limit tells us that reality itself is structured, purposeful, and astonishingly coherent. The very existence of a cosmic speed limit, that ultimate ceiling beyond which nothing can travel, reveals something profoundly reassuring about our universe. It is not chaos. It is not a random, lawless expanse where anything can happen without consequence. Instead, it is structured, elegant, and deeply ordered. Beneath the turbulence of stars being born and dying, beneath the uncertainty of quantum events and the enormity of cosmic distances, there lies an unshakable harmony, a logic to the way reality holds itself together. The speed of light, the constant c, is one of the clearest signs of that order. It is not just a number, it is the fingerprint of the universe's design. When we step back to truly reflect on this, we realize that the speed limit doesn't merely govern motion. It binds space, time, energy, and mass into one coherent whole. Einstein's relativity revealed that none of these quantities are independent. Space and time are two sides of the same coin. When you stretch one, the other bends to compensate. Energy and mass, too, are interchangeable, connected through that same constant c squared. Every interaction, every exchange of energy, every moment of existence unfolds according to this intertwined structure. It's as if the universe itself plays one grand, interconnected symphony, and c is the tempo that keeps everything in rhythm. In that light, the cosmic speed limit isn't a constraint at all. It's the framework that allows everything to work. It's the rule that ensures consistency across billions of light years and billions of years of time. A photon leaving a distant galaxy billions of years ago travels at the same speed as one emitted from your phone's flashlight today. It's the same constant that dictates how atoms hold together, how light bends around a star, how gravity interacts with time. C links the smallest particles to the largest structures in the cosmos, from quantum fields to the curvature of space-time itself. This remarkable unity tells us something extraordinary about reality. Everything is connected by the same laws. The expansion of the universe, the ticking of an atomic clock, the flicker of a supernova, the pulse of your own heart, all follow the same fundamental patterns. There is no separate physics for the heavens and for Earth. There is no special exception for matter, or energy, or life. The same cosmic constant that limits a beam of light also underlies the relationship between the mass of your body and the energy of the sun that sustains it. If there were no speed limit, if information and energy could move freely and instantly, that deep unity would vanish. The laws of nature would lose their consistency. Events could occur out of order. The flow of cause and effect would disintegrate. Every observer might experience a different, contradictory version of reality. The universe would no longer be a coherent, shared structure, but a fractured mosaic of disconnected perspectives. The light speed limit, far from being a restriction, is what creates the common reality we all inhabit. It ensures that space, time, and causality weave together into the seamless fabric we call existence. This realization changes how we think about the universe and ourselves. It suggests that we are not separate from the cosmos, but participants in its structure. The same constants that shape galaxies shape us. The light speed limit defines not just how we move, but how we experience time, how we age, how we perceive reality itself. Every breath, every heartbeat, every photon that enters your eyes is bound by the same unbreakable law. And there's something profoundly humbling about that. The universe doesn't owe its stability to chance. It owes it to structure. Its laws aren't arbitrary. They're expressions of symmetry, balance, and unity. Physicists often talk about symmetry as the language of nature, and C is one of its most elegant examples. It ensures that the laws of physics are the same for everyone, everywhere. whether you're standing still, orbiting a star, or flying near the speed of light. It guarantees fairness in the cosmos. No preferred places, no privileged observers. Every being, every point in space-time is subject to the same beautiful order. That's what makes the light speed limit so profound. It's not a wall keeping us from reaching the stars. It's the scaffolding that holds the universe together. Without it, there would be no relativity, no consistent flow of time, no conservation of energy, no coherent physics at all. The laws that give rise to galaxies, planets, and life itself all depend on this universal rule. In a very real sense, the speed of light is the heartbeat of the cosmos, the pulse that synchronizes every event across the tapestry of space-time. When we measure it, we are touching something fundamental, something that transcends distance, scale, and time. It connects the beginning of the universe to the present moment and binds every corner of creation under the same mathematical truth. And yet, beyond the equations and constants, there's something almost spiritual in this realization. The existence of a cosmic speed limit tells us that the universe is not arbitrary or chaotic. It is purposeful, governed, ordered. It has a rhythm. The speed of light gives that rhythm meaning, ensuring that every cause leads to its effect, that every journey unfolds in time, and that every observer can find their place in the same shared reality. So when we look at that simple number, 299,792 kilometers per second, we're not just looking at a speed. We're looking at the key to why the universe holds together. We're looking at the principle that makes understanding possible, that turns chaos into cosmos. The speed of light is not just a boundary. It is the thread that stitches space, time, and existence into one unified whole. And as we reach the end of this journey, this exploration of why the universe has a speed limit, we return to where we began, but with new eyes. We see that this limit is not a restriction, but a revelation. It's the law that keeps the stars shining, the galaxies turning, and time flowing. It's the sign that reality itself has a heartbeat, and we, fleeting and fragile as we are, live in tune with it. At the end of it all, beyond the math, beyond the theories, beyond the experiments that stretch across centuries, there remains something almost sacred about the speed of light. It is not merely a number we jot down in physics textbooks or a constant that shows up in equations. It is, quite literally, the heartbeat of the universe. It is the rhythm that keeps time and space in balance, the pulse that guides everything from the birth of stars to the firing of neurons in your brain. Every signal we send, every sunrise we witness, every flicker of light that reaches our eyes, all of it moves in step with this cosmic tempo. When you look up at the night sky and see the stars twinkling, you are not just witnessing light. You are witnessing time in motion. Each photon that reaches you began its journey long ago, traveling across unimaginable distances at exactly the same speed. 299,792 kilometers per second, unwavering, unchanging. Some of the light that touches your eyes tonight left its home before humans existed, before Earth was even what it is now. Yet it has obeyed that same law the entire way, carrying with it the story of the cosmos. This is what makes the speed of light so profound. It connects every moment, every place, every being in the universe through a single unbreakable thread. The light from a distant galaxy, the glow of a candle, the energy that warms your skin from the sun, all are part of the same universal flow. The same constant that governs the motion of those ancient photons also determines the very structure of space and time you inhabit right now. You are not separate from that rhythm. You are made from it. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. that there is an underlying order to it all. And the speed of light, c, is the embodiment of that order. It's the bridge between the tangible and the infinite, the rule that ensures the universe remains both mysterious and understandable. It tells us that even though the cosmos is vast beyond imagination, it is bound together by consistency, by harmony, by an unspoken agreement written into the laws of existence. Think of it. Every beam of light that has ever existed, from the first burst after the Big Bang to the faintest glimmer from a dying star, has moved at exactly the same pace. Never faster, never slower. Across billions of years and billions of light years, through the rise and fall of galaxies, the universe has kept its rhythm perfectly. That is what makes our cosmos not just vast, but profoundly beautiful. It means that there is pattern in the infinite, a cosmic choreography that never falters. And somehow, against all odds, we're part of it. We, fragile beings of carbon and curiosity, have evolved to not only witness this cosmic rhythm, but to understand it. Our minds, built from stardust, have reached out and grasped the laws that govern the stars themselves. The same light that shaped the galaxies has illuminated our thoughts, inspired our discoveries, and given us the power to comprehend our place in the grand design. So when we ask, why does the universe have a speed limit? We're really asking something deeper. Why does the universe have order? Why does it make sense? The answer lies in that constant, that ever-faithful speed of light. It's not there to hold us back. It's there to hold everything together. It's the framework that allows reality to exist, to unfold, to endure. It's the reason time flows, the reason energy transforms, the reason we can experience the passage of moments and the beauty of change. In a sense, every second of your life, every heartbeat, every breath, is an echo of that same cosmic rhythm. You are living within the boundaries of light speed, and because of that, your experiences have meaning, sequence, and depth. Without that limit, there would be no before or after, no stories, no evolution, no memory. The light speed constant doesn't confine us, it defines us. So as you watch the stars tonight, remember that their light is not just illumination, it is communication across time, a message from the universe written in the purest language there is: motion, energy, and constancy. Every photon that touches you carries a fragment of the cosmos's eternal heartbeat. Every shadow, every reflection, every shimmer of light is a small, sacred reminder that you are part of something vast and harmonious, something that moves with unyielding grace and precision. The speed of light is not just a number, it's a law woven into the fabric of existence, the rhythm to which all of reality dances. It tells us that the universe isn't random, it's purposeful. It tells us that chaos has limits, that order prevails, that every movement, from the turning of galaxies to the beating of your heart, is part of the same cosmic melody. And when you pause, just for a moment, to feel that, to realize that you are a small yet essential note in that grand universal song, you can't help but be filled with awe. Because in that instant, you understand that reality itself has a built-in rhythm, and somehow, miraculously, you are part of it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.